Hi, everybody. My name is Robert Schimkowitsch. I started programming when I was about 8 or 9, became a professional software engineer, and then joined a company creating software for hydroelectric power plants. That was last century. My specialty is user interfaces and visualization. I used to write all that code myself. Nowadays, I write choice pieces of it and otherwise support some juniors doing their work. And surprisingly, they are not named Claude or Gemini. If you come to Vienna, you can see the other part of my C++ life because I co-founded a user group there. So everybody is welcome to attend, or maybe even to give a talk there. If you're interested, please get in touch. Over the course of the years, I've solved similar problems more than once, and this has shown me how my own coding style evolved over time. So when I look at a piece of older code now, I always ask myself, would I write this differently today? Imagine you are me, and we have just stumbled over this piece of code. I'm not looking for in-depth analysis here, just give me your gut feeling. Who likes this kind of code? And who does not like this kind of code? I don't like it, and I'll tell you why. It interleaves the core functionality with error handling, making it really hard to see at a glance what the function does. In addition, we have this weird bool return type, which is actually a success flag, not the actual return type, which is hidden at the end of the parameter list. We're not going to mix those two up, are we? We could use exceptions and would look much better, except, of course, we have to throw somewhere and we have to catch somewhere. And if we catch the wrong type of exception, we crash. And also, should we use exceptions for the main errors? I'm not sure that's the right choice. At least not the choice for everybody. So let's see, what else could we try? We could just put the error flag in a class member. That way, everybody can just read from it, write to it. Looks great, right? Except we just move the checks around, and if we forget them, we get some really funny behavior. And congratulations, we have just created our own little dependency hell. Everything now depends on the single error flag, no matter whether it was related before or not. This is called shared mutable state, and it's poison to local reasoning and thread safety. So let's take a step back and fix the return type issue first. And we can actually combine the success flag with the actual result into an optional of the result type. That way, there's no ambiguity anymore. If the optional is empty, that implies failure. Otherwise, we can use the value. And then we throw away all our if statements and let optional do the work for us. This way, the sequence of the function is plain and clear to be seen. Also, we cannot forget about the error handling because optional does it for us. This is a monadic operation in action. I've set myself 3 goals for this talk. First, I'd like you to understand what functors and monads do, what they do, not what they are. This is a talk about practical usage, not so much about theory. Second, I want to show you the monadic operations that come with the standard library in C++23, and after this talk, you should have no big trouble using them. And finally, if you find the topic interesting and worthy further investigation, I will give you enough leads and references to do that. All the code that you find on the slides themselves, and a lot more resources you can find on the GitHub. I will share the link towards the end of the talk. And please keep in mind that the code that you see on the slides is simplified. So if you want to play around with it, please either download from the GitHub or use the compiler explorer links that you'll also find there. I'll take questions at the end of the talk, and otherwise, please catch me in a break. I promise I won't bite, I won't even nibble. And did I mention I have children? I got rid of the dinosaurs, but there might still be unicorns hiding in these slides. All right. I promised monads, and now I come with functors. What's going on here? Well, as it is, functors are something of a basis for a monad because monads have all the properties of a functor, but a functor is simpler, so it's reasonable to start with a functor and then move on to monads. And if you think now, oh yeah, no, I know what a functor is, it's this collaborator thingy, you're not wrong, that's called a functor, but this is not the functor we are looking at now. So what are we looking for? Let's start with a little story. Once upon a time, there was a little sequence of code, and it consisted only of two functions. One, to calculate the area of a circle from a radius, and the second one, to format an area nicely as a string. They were combined so you could pass a radius and get the formatted area of the circle, and everything was good. Then a developer came, and she brought a vector of radii, and obviously she wanted a vector of formatted strings. No problem, they said, we'll just make a loop. And inside the loop, we will pretty much do what we did before. But then one of the functions said, this does not feel right. I'm sitting here together with code that knows nothing about circles and areas. It has nothing to do with me. I fear we have violated the single responsibility principle. And when I asked the seer what he sees in the future, he said, code duplication. How much better would it be if maybe somebody could transform us poor functions so we can handle vectors? Like maybe we create a new function and we use the old function as a parameter. The new function would accept the vector of whatever parameter type the old function accepted and would return a vector of whatever parameter type the old function returned. So for a format area which accepts a double and returns a string, the new function would now accept a vector of double and return a vector of strings. Then we can combine those new functions and use them on a vector. The vector aspect is only implemented once here. This is one way a functor can look like. I'd like to show you a different way, one that more resembles a container. As we see, this is not necessary to become a functor, but sometimes it's convenient. In this type of functor, we have a class that holds the data we want to transform in the next step. Here we pass the function that can transform a single item into a member function, which will apply this to all the items in the vector. The result is a new functor with the new data, so we can immediately repeat the process. So again, the vector aspect is only implemented once. Both versions are functors and both solve our problem. But let's take a look at what functors do conceptually. And for that, I would say we have one category which I would call like single values. So the radius, an area, a string, and we have the functions that bring us from one to the other. On the other side, we have a category of what I would call vectors. A vector of radii, a vector of areas, a vector of strings. And obviously what we want is we want to come from one to the other. And how do we do that? We borrow the function from the single value category, apply functor magic to apply to the whole vector, and then we can repeat the process in the next step. And the nice thing about this, we are not bound to vector. We can just replace it with something else like optional. Our single value functions don't even need to know about that. This is nice separation of concerns. Now let's add a little theory, because functors have to follow two rules. The first is the rule of composition. Because we could compose our two separate functions into one single function that immediately takes a radius and outputs the formatted string. And of course, we can apply it via our functor. So we get a vector of strings. And it has to be the exact same vector as if we went through our pipeline stage by stage. This is guaranteed. The second rule says that identity needs to be preserved. Let's use a different function, std_identity, which takes an argument and returns it unchanged. So, of course, we can also apply it via our functor. So we go from vector of radii to obviously vector of radii. But the important part is it has to be exactly the same thing, which means that the functor is not free to use internal or external state to influence the result that you get. So to summarize, a functor allows us to map functions into different categories, like from single values to vectors to optionals and to other things. And they follow the rules of composition and identity. As we've seen, functors can be implemented in different ways. And this implementation does not make them a functor or not. It's the behavior and the guarantees following those two rules. Now, I've used vector as an example to show the benefits of using a functor, but of course we might want to use other containers or general ranges, and we don't want to write such a functor ourselves. We don't have to, there's std ranges views. When we look back at the vector example, specifically at the classical implementation, we can get the same thing with something like this. Now, let's take a look at what happens. Std ranges views offers a transform function which takes two arguments. First, the input range, and second, a function which is then applied to each item. The output is a new range, or a view in this case, which we can use as input for the next transformation. Now, this notation with inner and outer transform is pretty confusing as the pipeline grows longer, so the pipe operator to the rescue, we can, the code above and below does the same thing, so we can write it with the pipe operator, and I find this a much more natural way to express a pipeline. So we start here with an input, with a sequence, and the pipe basically injects this as the input for the first transform. And the result of the first transform becomes then the input for the next transform. But there's two questions here. What do we actually return from our function? And what type is the view? Let's answer the second question first. Because a view is not a container, it does not hold the data, typically. Think of it like a recipe. It's not cake, it tells you how to get cake. You still need some ingredients, which also means that views typically do not own the data. There are cases where they do, but don't assume that they own the data, so be careful about lifetimes. And views evaluate lazily. What does that mean? When I construct a pipeline, nothing is yet evaluated. It happens when I start pulling data out of the view, for example, by iterating. And this is, by the way, the type that we get, and it varies by compiler, so auto is pretty much the only way to make use of this. And this has some implications. Because if you return a view from a function, you have to use auto, which means you cannot separate declaration from definition into different files, and this can spell trouble. Because this is still not a function template. The return type is actually well defined, we are just too lazy to type it. So what I recommend, mark such functions inline, don't overuse them, and keep the scope where you use them small so you still have view of the lifetimes. Alternatively, we can just return a container, and that's really easy with C++23. We can use std ranges too, which converts to a container of our choice. Can be standard library, can be third-party library, as long as it fulfills the interfaces. This way we get a clean API. We can again separate declaration from definition. What we lose is the laziness, because now everything has to be evaluated in that single line and filled into the container we need to allocate and so on. So to summarize, views are more like a recipe than the actual data. So they typically do not own the data, or at least assume they don't. So be careful about lifetimes, use auto, and they evaluate lazily. And there are traps. I mean, of course, we are talking about C++ here. So depending on compiler, build settings, and so on, this will crash, output garbage, or maybe even work. Let's walk through it quickly. We have a very simple struct which contains of 2 integers and 1 string. And we have a function which is called getNearestEntry, which takes an integer and returns a C entry by value. Implementation is not important. What we want is we want to go from an integer to a C entry and finally just grab the M entry member, the string, so that we can print it. And how we do that is we use ranges views and we do a transform. with get nearest entry, which brings us from integer to C entry structure. And in the second transformation, we just use some text because that's what we want. But the problem is that we are now sitting with a dangling reference, because the C entry that we got in the previous stage was just a temporary. It's a bit like this function here. You pass something by value, and then you return a reference into it, which is not going to work well. However, it might be less obvious in this pipeline style code, so be careful and always use sanitizers. As you might have noticed, passing callables is an important aspect of using functors, and the same goes for monads. When I started with this coding style, I sometimes had difficulty fitting my function into the functor of my choice, and I want to spare you some of that difficulty and show you the most important ways to feed your functors. So we can use free functions, and that's nice and easy as long as they don't have any overloads. We come to overloads later. And we can do the same thing with static functions of classes. Just add the class name for qualification. And then there are inline lambdas, which are super useful if you have a small snippet of code that I don't want to reuse in multiple places. So it's best for those use cases. And for example, it can help me with overloaded functions. Because while the compiler cannot decide which overload to pick, when you wrap it in a lambda, the compiler can usually figure it out, unless there's really a conflict of the overloads. And then there's typical issues that you need to overcome when you work with functors, like they only accept one parameter, they only provide one parameter, but you have multiple parameters in your function. Well, you can wrap it in a lambda and provide the extra parameters via the lambda capture. Then we might want to call a member function. So let's say our functor gives us an object instance, and we want to call a known member function of that. Yes, we can do that with a lambda. And let's say the functor gives me a value, and I want to call a member function of a known object instance. Well, we pass the object instance via lambda capture, and we're good. We can use lambdas multiple times and give them names, which is sometimes even makes sense for single use if you want to document what it does. And you can use function objects, which are very similar to lambdas, but which gives you a little bit more flexibility even. And an interesting option is to allow the user to inject behavior by, for example, accepting a std function. Std function is a wrapper that wraps any callable with a certain signature, return type, and parameter types, which are the template arguments. And then you can just call this std function as part of your pipeline. Of course, you can do the same thing with template arguments. You can pass a callable as a template argument. And if you want to be sure that it's the right match, it has the right signature, then you can use, for example, a std invocable concept to check that. There's trade-offs, obviously, between std function, which has a bit of runtime overhead, and templates, which has like a bit of code complexity overhead. But to summarize, there's many ways to feed your functors, and I've by far not listed all of them. Lambdas are a great basic building block, the Swiss Army knife, as I would say. And then add std function to inject behavior, and you have a really good basic set. Now that we know about functors, we can talk about monads. Because monads have all the properties of functors plus something extra. But let's again start by looking at how a monad helps us solve a problem. And let's say we have a tree-like structure, and in that tree-like structure we have nodes. And we have a function called getChildren. And since a node can have multiple children, it will return something like a vector of nodes. And then I want to get the grandchildren, and that won't work, because getChildren is not equipped to handle a vector as input. So what do? Let's try with functors. So we start again with our vector of nodes, and then we transform, and then we get a vector of nodes. Our next transform is not going to be happy about that. So we invoke monad magic, we join the vector, so we make the vector of vector and flatten it into just a vector. And this allows us to continue. So we can do the transform again, and we can do the join again. So for our very practical purposes, a monad is just a functor with the ability to unwrap levels of nesting. Very hand-wavy, but enough for our purposes. You typically cannot unwrap the last level of nesting, at least it's not guaranteed that you can. Maybe you can for some. Rules for composition and identity still apply because every monad is a functor. And as we will see, the functions transform and join are often combined into a single function, which differs by name. But now let's leave theory behind and look at examples. It has been said that a compiler is a tool that takes files as input and returns diagnostics as output. Let's ignore the fact that it might also produce something useful like an object file and focus on getting and printing those diagnostics. And so I have a function which allows me to print a single diagnostic. And then I have a function to compile a single file, which obviously gives me multiple diagnostics, would be boring otherwise. And then I might want to compile multiple files. So I said, okay, let's say I have a project, whatever that is, and it contains multiple files. And this would be my classic style loop implementation. So I loop the projects, I get the files in the project, I loop the files, I get the diagnostics of a single file, I loop the diagnostics, and then I print them. Who uses code such as this? Okay, how else could we do it? With std ranges views, it would look something like this. Here we start with the projects. Then we transform them into files, which gives us a vector of files. So we join or flatten. Now we have a vector of files. Now we can continue with the compile. And this gives us now a vector of diagnostics. So again, we join, giving us just a vector of diagnostics. And now we can loop the diagnostics and print them. So here are both versions, top and bottom. What do you think? Which one makes the intentions of the author clearer? Now, do they behave differently? Functionally, no. They call the same functions in the same order with the same parameters. There are, of course, differences in performance and other aspects. But now I'd like to sidestep a little and talk about the topic of using functors and monads and specifically ranges views safely. And in my view, pure functions are a key to that. Who knows what a pure function is? For all the others, I'll explain in a couple of minutes, but let's first look at the motivating example again. Here we start at the bottom with a vector of numbers. And what I want is a view of those numbers multiplied by 2. And I use a function to get that. The function is above. Get multiplied view takes range as an input and a multiplier. And inside the function, I have a little helper lambda, which handles a single item and which gets the multiplier by lambda capture. And then I just return the view that I need. And back at the calling side, I print this view, doesn't matter how exactly. And what do we expect? So 2, 4, and 6 times 2 is, okay, probably not that. But let's see where it went wrong. Okay, so I pass the multiplier by value, which is, I guess, fine for an integer. And then I capture it by reference. Okay, that sounds a little fishy, but should be okay. Oh, but the view is lazy, which means my lambda will be invoked after I have already left function scope. So I'm sitting again with a dangling reference. Now, this example is specific for std ranges views, but in general, when you use functors or monads, you have to be aware that they control when your code gets called, how often your code gets called, and in what context your code gets called. So how do we avoid bad usage of our own code? I see 2 choices mainly. You can study the fine print of the functor and monad of your choice and hope that these guarantees don't change over time. Or you can make your own code safer by making it purer. And That's the option I want to explore. So what is a pure function now? It has mainly two properties. It will give you the same result for the same input, and it has no side effects. Okay, what does that mean? Let's say we have some kind of function which has some inputs and an output. Assuming you had infinite memory, could you replace it by a lookup table? And if the answer is yes, then we're good on the first requirement. Okay, what does no side effects mean? It means we don't write to memory outside of our own stack frame, and we don't trigger other side effects such as I/O. Pure functions have a lot of advantages. They're really easy to reason about. You just have to look at the function, you can understand what it does, how it does it. You don't need any global information. It's easy to write unit tests for them. As you might imagine, you can take a chunk of that lookup table and verify the function against that. And also, if it's really, really pure, it's also inherently thread safe. While pure functions are useful in combination with functors and monads, they are also valuable on their own. So imagine you had something like this, a function that interleaves complex logic with side effects, which typically makes it really hard to unit test. What I like to do is I like to split it into one function which takes as much of the complex logic, pure logic, as possible, and a second function which executes the side effects based on the result of the first function. And then I might add a wrapper so that to the outside world it still looks like a single function. Now the pure function is easier to test because I can take that lookup table approach, but also the execute function is typically easier to test because now I have an interface to control which side effects I want to trigger, and then I can verify that these side effects actually happened. Okay, let's have a little quiz. I will list some functions from the standard library and you tell me whether you think they are pure or not. Let's start with stdmax, maximum of integer and no custom comparison. Who thinks this is pure? And who thinks this is not pure? Yes, this is pure. Next is stdfill, a function for filling containers or ranges. Who thinks this is pure? Who thinks this is not pure? This writes to memory outside of the stack frame, not pure. Next is std system clock now. Who thinks this is pure? Who thinks this is not pure? Yeah, good luck writing a lookup table for that. Then we have stdsyn of double, calculating the sinus. Who thinks this is pure? And who thinks this is not pure? This might actually depend on your implementation, but actually it should use the global rounding modes, so it's not pure. Then we have stdups, calculating the absolute of an integer. Who thinks this is pure? And who thinks this is not pure? Well, it's theoretically pure, but then we have int min, and it's undefined behavior. What happens when we call it on int min? So can we say it's pure? I'm not sure. So what I wanted to point out with this quiz is that purity is not a black and white thing. There is some gray areas in between. And while pure functions help us write correct and safe code, it's often not reasonable to make a function completely pure. So I take a very pragmatic approach, make them as pure as is reasonable and necessary for your use case. So looking back at our initial example, we could argue that one of the problems is that the lambda is not pure. It depends on outside state. And we can improve that by changing the capture to by value. It's still not really pure, but I don't care, it works now. In the example so far, I've used functions that did not need to handle any kind of error or failure. And as we all know, this is like production code is, not really. So we have to consider error cases, and if for at least some part of our code we don't want to use exceptions for that, we need alternatives. In the following sections, I compare a value-based bool return approach with std-optional and std-expected. And our example is this. We have some database or storage structure, doesn't matter, and it contains very different types of data. For example, trends, images, and tables. And when you look at the table more closely, we can identify a column by index or key, and we can do the same for the row, which gives us a cell. And then we can look into the cell and see, does it contain a number? And if it does, we can check if the number is negative. So this is what we want, a function that tells us whether a number inside a table cell is negative. What could possibly go wrong? Well, the key into the database might be invalid. It might be valid, but not a table. The index of key, the index of row or column could be out of bounds. It might not be a number. And then finally, we have one stage where everything should be fine. Check for negative. And this would be a classic way to do that. So we have a function called getElement, for example. We pass the database key or handle. We pass the key to the element that we want, and then we receive an element by reference. And the bool return value of the function tells us whether it succeeded or not. I hate those because they are not composable. Then we have getTable, which extracts the table data from an element. Again, the bool return value tells us whether it succeeded. Then with getCell, we need the cell location as an extra parameter. And then finally, getNumeric cell value, which should give us an integer if the type is correct. Anybody has a flashback? You may have seen this code before. So let's quickly walk through what it does. So we create a C element on the stack and ask getElement nicely to fill it for us. Then we check the return value and ourselves exit on failure. Then we do the same with the table, create table on the stack, ask getTable to fill it, only exit on failure. And the same for the cell, and the same for the integer value. And finally, we are in success territory, and we can check if the value is negative and return with success. Now, how would we write this in a more declarative monadic fashion? We change our interfaces of our functions. So instead of returning bool, we combine the actual result type with std_optional and return an optional to the result type. Now, if a function fails, we simply return an empty optional. And if it succeeds, we return the element or the data wrapped in an optional. The same goes for getTable, getCell, and getNumeric cell value. And for the sake of completeness, I added another function, isNegative, which of course is not strictly necessary, could be a tiny lambda. But the interesting part is it does not return an optional. And the reason is because this function itself does not fail. So we just return bool. And then we start our chain by calling getElement, the first function. And it returns an optional of our C element. What this allows us to do is to call the next stage of the pipeline conditionally. That is only if the optional now contains a value. We do that by calling end_then and then passing the function that we want to use to convert further. Since we're talking about values that may be there, this is also called the maybe monad. Now let's assume that getElement succeeded and also getTable succeeded, so we have a table wrapped in an optional. Now, there's no join here, or is there? I mean, I don't see anything. So why do I call this a monad? And when we look at the signatures of the function, we might get an idea what's going on here. Because what happens is that getElement returns an optional of the element, but getTable accepts just the C element, not an optional. So somehow we have unwrapped a level of nesting. And what actually happens is that end_then is exactly the function talked about. It combines join and transform into a single function and does both things for us. Back to our code. So we pass the table into and call end_then with getCell. Now getCell needs a second argument, the location, so we wrap it in a lambda like we saw before. And let's assume it was a bad location, so now our optional is empty. So getNumeric cell value is then bypassed because the optional is empty at that stage. but we still get an optional of integer, an optional of the correct type. It's just as empty as the input was. Finally, we have is negative. And is negative does not return an optional, so we cannot use and then here. It's basically a transformation. We want to transform an integer into a bool telling us whether it's positive or negative. And so that's what we do. We call transform. So what can we do with an optional? Let's see some basic operations. We can check if it holds a value. We can access the value. If we try to access an empty optional's value, it throws an exception. We can also simplify by moving the assignment into the if statement. This way we can directly check on assignment whether the optional holds a value. And we can simplify further. For example, if we don't care if it holds a value or not, we just want to fall back to a default value, then we can use value or. Now let's have a little poll. Who prefers the classic way of code? And who prefers the monadic way of code? Loaded question, I know. But okay, fine, but what about logging, actually? I mean, let's say I want to do some logging here. And then happens to have a sibling function, which is called or else. And or else works exactly in reverse. It will call our function if the optional is empty. Since empty is our indication of failure, we can use that. Why is it a function? Is my log function a function template? Because it has to return an optional of the correct type, and it cannot otherwise know which type it would be. I mean, if you know exactly the type, you don't have to make a function template out of it. But we have a problem. So let's say an error happened up there in getCell, and we can catch the error because we get an empty optional, but we have no idea what happened and where. This is probably not good enough. Fortunately, C++23 came with std_expected. So what we do is we change our functions to return std_expected instead. Now std_expected has two template arguments. One is like before the value, and the second one is error information. Now, when a function now fails, it returns an unexpected, which is the error type of expected. And we can choose what error type that is. So I created a simple error type, which accepts a message as a constructor argument. So I already know what happened. And what I can also do in the constructor, I can use the stack trace library of C++23 to capture the stack. And so I know what happened and where it happened. If you're interested in the stack trace library, you will find links on my GitHub. If everything's okay, we return our value wrapped in an expected as before. And the chain is identical. There's no change here, because and then works also the same way as for optional. So if I have a value, and then will call my next function. And if an error happens, I will now hold error information. And because of that, the next function will be bypassed. My error information is retained. And at the end of the pipeline, I can shove it into my log function. So this is how it looks now. The log function now receives the error type. And so, for example, if I had the error in getCell, the information is carried down all the way to my log function. And now I can do some useful logging. And also the log function has to choose what it returns, because it also returns an expected. Now I can just pass through the error that I had. I could amend the error information, I add something to it, or I could even fall back to a valid default value, which I probably would not do for a log function. Usage is very similar to optional, so I can check if it holds a value, I can access the value, and now alternatively I can access the error. An expected always holds either a value or an error. Again, we can check directly on assignment. And again, we can use value or if we just want to fall back to a default value in case of error. And there's one more thing that you might need, because sometimes you come up with expecteds with different error types. So if you want to convert an arrow type, all you need to do is still expected transform arrow and a conversion function which accepts A and returns B. That's it. Now we've seen how you can use optional and expected to build a pipeline where each function has to succeed. Sometimes we want the exact opposite. We want to call a few different functions until one of them provides a valid value. And then we want to run with that. And that's easy to do with optional. So for example, I want to start an application and I want to figure out what UI language the user wants. And we have given the user 3 ways to specify their UI language. So they can do it via command line, they can do it via registry or a similar system, and they can do it via environment variable. And then I have a fallback in case nothing of those work. And this is the whole pipeline. So in this pipeline, the first function that provides a value wins. So let's assume that getLanguage from command line failed, our optional is empty. Because of that, or else we'll call our next function, getLanguage from registry. Let's say that one succeeds. So now our optional holds a value. Because of that, or else we'll bypass the next function, getLanguage from environment, and we keep our value as before. Had we been empty at that point, value OR would have provided us with the default, so we are guaranteed to get a valid non-optional value at the end. Maybe some of you noticed that I put monad in quotes in this section, and there's a reason for that. When we look at what functors and monads give us, they allow us on the one dimension to go from optional of A to optional of B to optional of C. And in the other dimension, they allow us to unwrap, that's the monadic aspect, from optional of A to optional of A. And as we have seen for optional, we use and then, which kind of moves diagonally across this table, doing both join and transform. Now, what does this have to do with or else? Nothing at all. With or else, we start with a type, we stick to the type, we don't move across types, wrappings, nothing like that. This is not a monad. It might be called something like a monadic style operation. It's still very useful sometimes, so I wanted to include it in this talk. I talked now a lot about how great functors and monads are. So is everything pink unicorns and rainbows? Sometimes life does not work that way. So this is something that might greet you when you start firing up your compiler with enthusiasm and yeah, what does it mean? Actually, AI is sometimes pretty good at figuring that out, so that's worth a try. But I want to give you some first aid so you are faster than typing your question into a chat. So the most valuable information is at the beginning and the end of the compiler error message, typically. And then it really pays to go through a few common causes for these error messages. Like, we use a function that has overloads. And as we've seen in the callable section, just wrap it in a lambda and you're good. Then we might accept or return the wrong type. For example, we accept an optional of t instead of t, and we mix up and, then, and transform. These become easier to diagnose when you use your types explicitly in lambdas, also the return type, instead of using auto. And then trying to pass views as const or const references will lead to problems. So just don't do it. You will find a compiler error cheat sheet on my GitHub. I'll share the link in a couple of minutes. But now let's move to another fun topic of debugging. And it's unpleasant unless you like stepping through half the standard library to go from function A to function B. So what would we need for a good debugging experience? Well, I want to start debugging, for example, where I start to loop a view. Then it would be great to see the pipeline, so I have some context on where we are. And then I want to step into my transform function, for example, and see what it does. And we can have the first and the last one, but we lose the connection in between. So what do we do? Question is, why do we use debuggers in the first place? And the answer is not always, but often that we want to find and eliminate bugs. But there's other ways to do that. I mean, what we have is a pipeline consisting of components which ideally are pure. This is a unit test stream. So what I would recommend is write unit tests for all the individual components of your pipeline, verify them, check which one does not conform, fix it, and make sure they are combined using strong types, which makes it very hard to build an incorrect pipeline that still compiles. And then you check it into your CI and stop worrying about this type of bug. Still, I sometimes like to do some interactive debugging, and you can do it because you can do the debugging of the individual for the loop and of your individual functions. The only thing you need is the connection between them. So just before you step into it, take a look at the pipeline to familiarize yourself with how it's connected, and it should at least be readable code. And then there is performance. And I made a couple of benchmarks. You will find the results also and the code on my GitHub. The results vary widely by compiler. The truth is, if you depend on the last nanosecond of performance, then you need to do your raw loops, you need to do your raw if statements, and you need to think about cache friendliness, SIMD, and other stuff. But the question is, let's say you're reading from a file, you're waiting for user input. What's this? You're waiting for user input, or you're waiting for data from a network. Do you really depend on the last nanosecond in your loop? Only you know what's true for your use case. I found that for my code, the majority of functions are not on a hot path. So there, it doesn't really matter if I use raw loops or ranges and views. But please take a look at my results, make your own measurements, draw your own conclusions. It's important to me that you know both the advantages and the disadvantages of using functors and monads. On the plus side, I see safety, clear communication of intent, composability, and separation of concerns. On the minus side, we have these ugly compiler errors, we have some issues with debugging, and we often have a moderate performance hit. I should also add that the monadic operations specific of the standard library have somewhat narrow use cases, so please don't try to apply them to everything. If your problem has the right shape for them, they are super useful. Now, while these monadic operations are somewhat narrow, the concept of functors and monads is applicable in a much wider context. So think of this talk as an invitation to explore further and see how functional techniques such as functors and monads can change your code design and allow you doing things that you could not do right now with other techniques. If you're curious about that, or you want to dig deeper on some of the topics, here's the link. I will also put it again during the Q&A session. Here you will find the compiler error cheat sheet, you will find the benchmarks, you will find all the slides, and you will find all the code from the slides, both for downloads and as compiler explorer links. As a bonus, you will get code examples that show you how to write your own monadic wrapper, and also how to combine two monads into one useful construct. But there's more, because I collected a lot of resources, and so you will find books and articles, you will find related talks, you will find papers, and a list of replacement libraries in case you can't use C++23 yet. Okay. It's time to wrap up. So let's take a look at our 3 goals and see how we did. I just show you the link to all the references. You should be happy for a week or a couple of weeks, I think. So I think we can check that one off. We talked a lot about what functors and monads do. We've seen how functor magic can help us lift out common repetitive code, separating the what I do from where I apply it. So you can code a function once and then use it for single values, vectors, optionals, futures, other things. And also without needing to change your code. Then use monad magic, add the ability to unwrap levels of nesting, and you can build pipelines that you could not build with functors alone. I hope this talk has given you an idea how useful functors and monads can be in general. And this is just a start. If you look at some of the references on some of the links on my GitHub, you will find out how much further you can take them. Check. And finally, we've seen examples of the monadic operations in C++23, and they are immediately useful for some common concrete use cases. You also don't need deep theoretical understanding to make use of them. I still recommend that you do dry runs, do tests, do measurements before you apply them to production code. Let's quickly see the patterns again that we have seen. So there's the ranges view monad for a pipeline where each input creates n outputs. There is optionals maybe monad. If you want to build a pipeline where you need to ensure that each function in the pipeline succeeded. Alternatively, you can use that expected if you want to provide useful error information in case of failure. And then finally, there's optionals default monad to grab the first usable result from a sequence of functions. These will help you write safe and readable code. The monadic operations in C++23. Thank you. And I'll put up the link again, and I think we have a few minutes for questions. Yep. So please make sure you use the microphone. Where is it?
Maybe you can repeat the questions.
Oh yes, I can do that. I can try that if they are not too long. Or maybe I've explained everything so well that there's no question. Or everybody's just tired now. I have no problem. So if you come up with questions later, please just... wait a second. We have one question at the back.
Thank you for your talk. Only slightly related, maybe you're checking the options.
Okay, so I will repeat the question. So the question was about optional of bool and whether it's problematic that it implicitly converts to bool. Interestingly, I mean, I've been thinking about this topic a long time now, preparing this talk. This idea never came up for me because somehow for me it was clear that the bool conversion of optional always only tells me, does it hold a value, does it not hold a value? But of course, there is some ambiguity there. So yes, what I do in practice in my code is that I prefix optionals with a lowercase o, for example. It doesn't matter how you do it exactly. So I immediately see, is it an optional of something or is it just the thing, which then easily identifies such problems. But of course, you're right. There's room for ambiguity. How do you prevent accidentally using vector of bool? I'm not sure it really applies here because, I mean, okay, this would go towards the ranges and views monad, and there's no vector behind. So basically, as I said towards the beginning, the ranges view monad, it does not store the values, so it does not create a container in behind that's hidden from you. Instead, it will provide the values on demand. Your functions get called when you hit the iterator++, for example. So in that view, there should not be a danger of accidentally using vector of bool. Do you have any online questions? Not? Okay. Well, if everybody's happy, as I said, just catch me in breaks. And thank you.